can give it over. Hey, what's going on, folks? All right, so you guys can hear me all right, and you guys can see me and everything. Let's go over Quad 4 Part 3, or Quad 7 Part 3, because somebody was asking a question on that. Is that cool with you? How is this homework so far? Is it not bad? Is it hard? Is it easy? What's up? It's pretty easy? All right. We're going to get into stuff that might not be too easy. My goal here is really to kind of take you along step by step, very slowly, very periodically, very methodically through the class, and hopefully that works. So let's do this. All right, so somebody was asking, oh, wait a second. I don't need to cover Quad 7 because that's for the other class. I'm sorry. I was thinking, for some reason I'm thinking I'm in Algebra 1. No, I'm in Algebra 2 today. Okay, cool. We'll do this then. So we're on exponentials, and we're on exponential 5 at this point. I'm going to do maybe maybe two more pieces of your homework, and we'll see the best way to go about doing this. To be honest with you, there's two kinds of math involved with this, with solving part B of this thing, and it's not hard. It's just it requires a tool that maybe I didn't teach you yet. So there's an easy, or there's kind of a different way to do it as well. I don't know if I'm making much sense. Anyway, has any of you guys ever heard of log or logarithms? Okay. In order to solve Part B officially using math and just math, you have to use logarithms or natural logs. And I know that it's a little bit weird, and in fact, to be honest with you, I'm skeptical as to whether or not we're going to be even covering it. I'm going to even cover that concept with you. It's actually a really awesome tool that you can use to speed up your life. But what I'm saying is, I'm going to probably teach you guys how to approximate it first, and then what we'll do is we will learn how to use the logs maybe later on, maybe. So anyway, let's try this one. Don't worry about it. All right, the amount of square feet in a certain kind of an invasive vine in a forest can be modeled by P of t is equal to 28 times 2 to the t, where t is the number of years after 1990. Okay, so the way I look at this equation is, remember, an exponential equation is f of x is equal to c times a times x, or c times a to the x power. Now, that doesn't necessarily mean that you have f of x. You could have, this doesn't have to be f, this could be p. And this doesn't have to be x, it could be a t. It still has the same form. We just changed the letters a little bit. The reason why we changed the letters is I'm assuming that capital P stands for plants. The number of plants as a function of t instead of x, because we're dealing with time. So in order to be more descriptive with the letters we're using, we changed the letters to be applicable to the problem we're doing. Does that make sense to you? Yes, we're good. No, we're not. All right, cool. So the first number here usually is, I think, the best way to see what, or to think about what that number represents is, remember, we looked at the graph, and what that does is it kind of changed where that thing lands, right? On the graph, this C right here kind of governs this point right there. And if you think about it mathematically, I mean, think about plugging in 0 in for t. What happens when you plug in 0 for t? What does your answer become? Yeah, exactly. If you plug in 0 for t, then a to the 0 power is just 1. So really, your answer becomes, so I should say p of 0 is equal to just c. Right? Because c times 1 is still c. And it doesn't matter what A is. A will, all that will do is, it doesn't matter what A is because anything to the 0 power is still 1. So C times 1 is C. So what does T equals 0 really represent? What it represents is, actually, I'll give you a second to answer that. Do you guys know, what does T equals 0 represent? If you don't know, say IDK. I just want to make sure you can hear me. All right. What it represents is this. It's the population at time equals 0. So in this case, it's how much the vine was at the beginning of time. When, before I started the clock, at time equals 0, boom, it starts. So apparently, this was the population back in 1990. It was the square footage of the plant in 1990, a certain vine or something like that. So we're looking at how big the plant was in 1990, and apparently it's 28 times 2 to the T. So it's 28 square feet or something like that. Does that make sense? Okay, so the population at time equals 0 starts at 28, but it doubles every 2 years. Now, how do we figure out the way, or how do we figure out how big the population is today? All right, so the way I would do that is I would just, they told us that this is the population of the plant, or maybe I should say square footage of the plant, or the size of the plant is 28 times 2 to the T, and we're waiting for today, and it's since 1990. So since today is 2015, this was all the way back in 1990, we're talking about raising it to the 25th power. So it's 28 times 2 to the 25th power. That's going to be a huge number. I think, let's see. Let's look at this thing. All right, here we go. Let's go over to Desmos. Okay, that would be 28 times 2 to the 25th power. 9395240096. 9395240096. So it is 939,524,096 square feet. Yeah, don't let that plant go on for 25 years. It's going to be huge. We cool with that? I mean, that really was just calculator work. You just plug that sucker into your calculator. All right. Now, here's the question. And to be honest with you, I almost feel like I don't know the easiest way to go about doing this. I actually kind of want to show you using the calculator that you're going to be given on your thing. So let's use this calculator and see if we can get to this thing. I'm basically going to go to the part where it says use this calculator from now on. I'm going to just open up the graphing calculator. I'm going to go to graphing, and I want to plug in, I want to model this function, 28 times 2 to the x. I know it said t before, but I mean I can kind of interchange those. I'll still be happy. Graph. All right. When I graph this thing, look what happens. It grows so quickly that it's hard to see this graph, to be honest with you. In fact, this thing doesn't do a very good job doing that. Let's go over to Desmos and see what we can get. Okay, that's a similar graph. Desmos does a better job at doing that. All right. So here's the thing. About how long do you wait if you want to go to 28 million square feet? How long do you have to wait to get to 28 million square feet? So we just got to find 28 million. That would be way back. There's 2 million. This is 20, yeah, that's not even close. 28 million, that would be, how many zeros? That's 6 zeros at the end, right? So it'd be 2, it's around here, maybe here. What are we at? 18 million, 19 million, 21, 28 million, there we go. Let's zoom in on that spot right there. Sorry. It's a little bit cumbersome. Okay. It's hard to keep this thing centered. Okay, we're too high. There we go, 28 million, it's right there. Zooming in some more. What I'm trying to do is I'm trying to see this scale real nicely. Okay, here we go. All right, here we go, here we go. So, what you're going to do is this. You're going to say, well, at year 0, it reaches here. At 28 million, what's the time that it takes to get to 28 million? And you can read that number right there. Can you see it? $20. Yeah, about 20. In fact, we can even zoom in a little bit more. Is it exactly 20? No. If we zoom in enough, we can even see it exactly. It's here's 19, here's 19.8. That would be 19.9. So this is about 19.93. No, 19 is down here. 20 is over here. So it's way closer to 20 than it is to 19. I would say about 19.9, and I can even zoom in and get really accurate on that. See, all right, so here's 19.92, here's 19.93, and that kind of stuff. Could you have just clicked on it and have it tell you? Yeah, you could. Not really. Not really. All right. That was really sloppy. Do you guys agree? Like, that was kind of tough to do. Because, oh, here's exactly 28 million. I didn't like it. What is a better way to do that? Let me think. Here's what I would do. All right. On Desmos, you could do this. You could go and click on that edit button and say, hey, I want to make that a table. All right. You can also do this on the calculator. All you do there is just click on table, and it will give you a nice little table over here. Okay. And then what I would do is I would start just trying numbers. 18. So over here, look, if I typed in 18, it gives me 18, 19, 20, 21. So I know that the number's got to be between 19 and 20. You see that? Because this is 29 million already. Making sense to you? Like if I were just straight up at 19 million, no, or 19, I would only be at, what is that? That's 14,680,064. So I'm wondering if you can get even more accurate with this thing and go 19.5. Oh, I see. Here's the game we're going to have to play. Is basically, we're going to just try typing in numbers until we get until we get that y value as close to 28 million as we can. So let's go 19.8. Okay, we're getting closer. It's 25 million. Let's go 19.93 as we guessed it to be. Oh, this is really close. 28. In fact, we can even go 19.935. I don't know, I'm just making this up. Oh, I see. The problem is the graphing calculator that I gave you doesn't take more than 3 numbers after the decimal place. So that's about as close as we can get. So I guess you can choose whether or not you want 19.93 or 19.93 or 19.94. Does that make sense? Okay, so there's 2 ways of doing it. One is graphically, the other is looking at a table. I honestly think that the table is the best way to do it. I'll be quite honest with you. I didn't actually solve it using that way. I just did this. I did, and this is not what I'm going to teach you now, but maybe it might be motivation to say, hey, when we get to this chapter on logarithms, that's actually pretty cool. Well, watch, natural log of 28, this is how I did it, divided by 28, close parentheses, divided by the natural log of 2, close parentheses. And my answer is 19.931568563, which is way more accurate than anything you guys could get. Because I didn't read it off the thing, I just used straight up math. You guys are thinking, wow, that's pretty cool. But I'll be honest with you, I think that if I were to teach you logarithms and all of those properties and how to do it exactly like that, I think it would confuse you more. So, my recommendation is this. When you're asked to solve a problem like this, then what you should do is you should probably make a table using a graphing calculator of some sorts. And then search for the x value that will give you as close a value to the y value as possible. Does that make sense? And then what I would do is I'd probably try to look at the graph of it and see if that gets you close. And since I'm asking you approximately, I would have taken the answer 20. I would have taken 19, even 21. But technically, the closest answer you can probably get to is exactly 19.9315. Wait, what was it? 19.931568599693. But even the graphing calculator won't really take you that close. So, you know, give or take. Does that make sense? All right, cool.